Okay, let's try to get a little bit of work done. First thing, let's my girlfriend took this picture, so let's throw this up on the internet. View and edit post, right? Yeah. Yeah. Put my Twitch URL. There we go. Yep. Okay, that looks good. That looks good. Okay, there we go. Let's throw that in there. Bam. Post publicly? Yep. And I believe that if we put Doged into the internet, we get memes, don't we? We get the memes. We get the memes. Excellent. So we're good. I know I'm old because this is old meme stuff, but you know what? Good enough for me. Okay. What about this? Let's just take this. Let's just take this. And something synergy. There we go. Something synergy, workforce productivity for an ever-changing, fast-paced world of tomorrow. Blah 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 blah. Cue music. Also, why corporate music sucks? Hold on, let's find this. Music with no soul. I'm an atheist, but there is a thing called music with no soul, right? Music with no soul, maybe? Let's try that. That might actually be what I'm looking for. Hold on. I know I'm kind of distracted here, but gotta get into the swing of things here first.
Are you an executive making a video pitch to win new business? Perhaps you're a team leader.
Yep, that's it. That is the thing. This is the Music with No Souls video, so we'll put that into our shortcuts. Yeah, this thing right here. Music with no soul. Bam! We'll call it Corp Music. Music Corp. And we'll also take that, and we'll put it over here. Alright, we're good. We're good. Let's just post that. Bam. Okay. People are gonna say, oh, you can't use LinkedIn for stuff. That should be like Facebook. Too bad, I already did it. Okay, so let's close that. Let's close Imgur. And let's go put this over here, and let's start actually writing some more test code, which I don't want to write, but the thing is you need a stable foundation, right? You absolutely need a stable foundation for whatever you're writing. You gotta write test code. Okay. Well, I disagree with the idea of test-driven development. That's not the same thing as saying I don't think tests are a good idea. Tests are a great idea. Okay, so let's look around here. So is this our big loop where, yeah, because we were talking yesterday about this. And this test code started out with a nice little table. And after we ran this, we decided to do some procedural tests. And for these procedural tests, we kind of hacked them together to make them work by just looking at these last 2 bits. So what we could do is, I think that we can do a next series of tests where we loop through everything at different step sizes, and we can do like a master procedural test, like a final one procedural get put test to rule them all kind of a thing. So what I'm thinking is master get put test 2021. So I'm thinking, actually technically it's not 20, it's not just 2021 lasts for a whole year, so maybe we should do this, right? Just make a note of the year. Okay. And then within here, we'll do our kind of like big boy test where we just go through like everything, and well, here. So let's just look up our variables here. I know we kind of like inlined a lot of these variable declarations earlier. What I'm gonna do is I'm gonna take some of these variable declarations and I'm gonna move them up to the top of the file, because we're going to use them in some of the other loops. So let's go and kind of just say, hey, variables, yeah. So I mean, this is the basic steps, but we're doing it multiple times, right? I'll kind of keep, actually, no, I'll keep this commentary kind of glued to here. Yeah, because that commentary actually is for the first test. Let's just declare variables over here. Throw in those variables that we want to use. And close off this section. So variables that we want to declare, and let's kind of grab some other ones because there was like a test index and a base offset or whatever. Yeah, so these guys here, we're gonna steal these here from here. We're gonna take those, and we're also gonna move those over here, right? And we're just going to so this is declared. This was all kind of stuff declared during the first test chunk, right? And also I erased the wrong thing. I erased the types rather than the my bad. So we'll get this. I guess this comment doesn't make as much sense because it's been moved from where it was originally declared, but whatever, we'll figure that out. So these things here, yeah, so the we want to take this, and we also want to take the test index and kind of get rid of that. And then over here, we want to paste this again, try again, right? And then we want like a int32 for the test index. Right, so we have the test index and this base variable and all that good stuff. And we want to align it somehow. I guess maybe like this, I guess, seems to be kind of how we're doing it. Make sure we end our statements with a semicolon. And we can also make a note of what this is, right? So this is the test index. This is the base offset to first test. Right, this is the base offset. We could say first test element index, right? Base. Right, so it's the base address, right? Canvas user view integer x, right? Over here, canvas user view integer y. Over here is the layer index, right? Layer index. Okay. Over here we have the offset okay. Canvas user view bits, 16 of them. Okay. Gotten. Right, so that's what all that kind of means, right? Now, we got a situation here where these comments are kind of like all over the place. I would like them to be a little bit more regular like that. I think that makes everything look kind of a little bit better. We can also do a dash line I3 x64. Kind of make a little section divider. Okay, so now we want another test chunk. I don't know exactly what we're going to call it, but before that, let's highlight some stuff in here. Just a few things, so that we can go down here for a second and be like, hey, this stuff here, we don't want to shadow these variables, so now we're going to get rid of the types in front of them. This got B16 looks like it was just declared, but it was not actually set to anything. So we could just set this to something bogus, right? So we could set this to 0x ff something, right? Some type of bogus value, or A, B, C, D, right? And let's go through all this. Let's make sure everything looks good. Okay, so we're going to do some stuff here. We're going to use the same get put commands, so we can define these again, and then undef them again. But before we go any further, we want to run the code again, make sure that it gets past this test. And if it gets past this test, we will add some more code. Okay. Alright, so right now, this is a failure for a different function. We can look up here, we can see that this function right here is the one that began and ended, the one we're working in, and that's fine. That function's working alright, it's not failing. So now we need to write some code for this test, and what we're going to do is we're going to go through this whole thing here at different step sizes and do a put get test each time. So we're going to take kind of like the code, we're going to take basically this code, and we're going to do it with different step sizes. So if we take, let's just steal all of this, right? Let's just take all of this for a second. Take it all. Let's paste it down here. Let's remove some of the commentary, right? So we have like a lot of commentary for some stuff that was going on, right? And right now, we need a different mask size depending on what our step size is. And mega test fail 2021, right? And alright, so you need some type of unique error message, unique to the entire code base. So, you know, fairly certain that's unique. I'm not going to worry too much about that. As long as I can find the error message very quickly in the whole code base, that's what I really care about, right? So, if we type a whole bunch of gibberish for an error message and we put the current date at the end of it, then as long as we are unique in terms of the entire year, right? So if we're unique for 365 days, we can start to be a broken record after the year resets, right? So for this code, we're going to add a CXCY location, a layer location, and an offset index location. We're going to put this payload. And then we're going to get the payload, and we're going to expect nothing bad's going to happen here, no matter what the step size is, because if we get input, we're never going to have to worry about memory stomps. Now, if we do all of this code here, and then we do everything over again, where we regenerate the B16 value that we're going to put down, but this time we just get the value without putting it. Sometimes the value won't persist if it got overridden, depending on what the tile size is. So we want to modify this to change the step size so that for different bit size cross sections that this code will always work. So we're going to take all of this, and we're going to indent it one, and the CXCY needs to have a different step size. So sometimes it's like +1, +2, +4, +8, and we need to create maybe an array. Array of step sizes might be the easiest way to go. So these are all int32s, I believe, right? So CXCY, right? We just decided to keep it kind of simple and make all of our things int32. So if we go up here, we see, oh, they're all U32s, except for test index, huh? Oh, no. These are U32s. Let's divide this for a second. Let's make an obvious division between the uints versus the uints versus the int32s. So yeah, CXCY, those are int32s. So let's create a thing that says declared during third test chunk, right? I'm going to create a third test chunk. And within this third test chunk, all I think we need here is kind of a step size, or a step amount. We'll say step amount, or STP. We could say offset, offset amount, or I do kind of like STP for step. Or we could do SA for step amount. I don't know. Doesn't really matter too much. Step amount. Step amount for looping, right? So we need a step amount. And then in the last test down here, what we're going to do is we need a table of step amounts, right? Table of step amounts. And that is going to have 8 entries for the different tile sizes. And we're going to initialize it with 1, 2, 4, 8, 16, 32, 64, 128, and what else? 128, yeah? You can also make absolutely sure that's everything, right? So So these are for the different tile sizes, right? So for the different tile sizes, we have tile size 0, tile size 1, tile size 2. Actually, let's do like tile size 0, tile size 1, tile size 2, tile size 3, tile size 4, 5, 6, 7, and that's not right. I'm missing something here. 1, 2, 3, 4, 5, 6, 7. Should just go all the way up to 7, right? So let's kind of adjust this to have the numbers kind of aligned with the tile sizes that they're looking at. And yeah, tile size 7, right? So let's actually kind of give this 3 zeros because the last thing has 3 digits, and we want to kind of be able to have everything nicely aligned when we're looking at it. We're going to align these numbers with the 1s places, the 10s places, the 100s places, etc., right? So yeah. So this is TE. This is the tile exponent. Whereas these numbers here, right? These numbers here are actually the pebble size, right? So if we wanted to look at this and give it some type of meaningful number, or if we wanted to give it some type of meaningful identifier, then the meaningful identifier for these numbers that are all powers of 2s are the pebble size, or the size in pebbles, right? So we could do this as well, kind of put this over here like that, and just say right here, this is peb, right? So tile exponent, and this is peb for size in pebbles. So yeah, now we have a table SA step amount, right? So we can make a note of what table SA means, right? Table SA right here. And with table SA, we can go through this here, right? So we have a step amount, and then we should also make a... Let's just try to make this kind of simple as possible. So we also have a mask, right? We need a table of masks. And for different... right, so we're going to use parallel arrays. And we need different mask sizes depending on how many bits can be trusted. How many bits can be trusted for different step sizes, right? And when we're stepping at the smallest size, the only bit that can actually be trusted is 1, right? So we can say that or the first 2 bits. So and we can make a note of this, right? So we can go so there are 1, 2, 3, 4. 1, 2. Did I say 4? 1, 2, 3, 4, 5, 6, 7, 8. So these are 8 tiles, but it's 16 bits, right? So here's our 8 tiles. And the first mask, for the first tile size, the most granular tile size, the only thing we can trust not to be stomped is going to be the first 2 bits. And then we can keep on going. The more coarse we move, the more trust we have in terms of, hey, what's not going to be stomped, right? So we can keep on doing this, and we need these kind of mask values, right? So might as well just hard code these mask values, even though we could generate them on the fly, because it's more illustrative of what's actually going on here. The tile size exponent equals 0. Alright, so these are for the different tile size exponents, right? So if the tile size exponent is 0, then our step size is, 1. Right, and we should go all the way up to 7, right? 0 to 7, right? Those are our different tile size exponents. And when our step size is 128, we can trust that all the bits will be correct, right? Because we're going to basically move from setting a tile over here to setting a gigantic tile over to here, and there's not going to be any overlap, right? So here, the memory stomp is nothing. Nothing gets memory stomped. Here, this gets memory stomped, these 2 zeros. At this size, these get memory stomped, and so on until once you get to the most granular step size, the only thing that does not get memory stomped is this. So as we're writing these tests and iterating through it, depending on what the tile size is that we're using, depending on the tile size Josh is using as he is clicking around here, right? Because we're kind of emulating Josh going through here and clicking to set different tiles of different sizes. Depending on what size the brush is configured to, that's going to determine our confidence in what values aren't going to be overwritten or memory stomped, right? So we could make a note of this. Before we kind of do this, we can make a note of what the video is, and maybe explain this one more time, right? Okay. This is our master memory stomp test for emulating Josh clicking on the canvas to set various tiles of different sizes. That is a rough analogy because Josh's brush will never be loaded with all possible tile sizes that could be under the point in which he is clicking. Right? Okay, so what else are we doing here? Let's make some more explanation. So 27, 38, how about 42 to be cool? Okay. So what we're doing here is we're kind of clicking here and setting a payload of bits, a payload of 16 bits that defines all 8 tile sizes that could be underneath this pixel, right? And all 8 tile sizes are going to be stored in this data structure here. And so if I click here and the largest tile size is loaded into my brush, then it puts a gigantic tile over the entire canvas. And there's only one of them that can be right in this location. So if I click here and I click here, if I click here and then I click here to set the biggest tile, I'm going to have overwritten that tile information because there's only one of the biggest tile. However, if I click here, to set a quarter size tile, and then I click here, and then I click over here to set another quarter size tile, there's no information overwrite because this tile is a different tile than this tile. So what we're going to do is first we're going to step through at the most granular level, at the unit level, and when we set tiles this way, the only thing that won't be overwritten is the smallest tile. Then we'll step at a more coarse level, and when we step at the next most coarse level, we'll have, over here, we'll have 2 different tile sizes that are guaranteed not to be overwritten, right? And we keep on stepping at more and more coarse levels, right? And the most coarse level we can step at is here to here, right? So, or in terms of clicks, go from here to over here, right? And if we set a payload of tiles here and a payload of tiles here, none of them will intersect because the largest tile value covers this area for the first click, and the largest tile value covers this area for the next click. So we've created this mask to determine our confidence as to which variables or which tile sizes have not been, which tile values have not been overwritten that we can check when we are looking for the correctness of the code, if that makes sense. So this test here that we're about to do is this master git put test 2021-0126. This test right here is a copy of the procedural batch put then git test here. So it's a copy of all this code, but now we're going to put an outer loop around it and use these masks to do a more robust check. We can make a note of this and say, you know, C diagram, or actually C file, and C diagram. So we want you to look at a certain file and a certain diagram to really understand what's going on here. So this diagram has a name. It's really canvas user view. I mean, I guess technically this probably has a, yeah, that's good enough. If we call this diagram canvas user view, that's pretty okay. Canvas user view, and then also the other diagram we want to see is, because when we use the canvas user view to click into the canvas, it affects this underlying data here, right? So it affects the main space partitioning, right? So these are the two diagrams that you're going to want to look at to kind of understand what's going on. And different step of the larger your step size, the less tiles that get overridden. Each click you do lays an 8-tile payload specifying the tiles of each tile size exponent to lay down. Right? So that's what's kind of going on. Now, maybe that's not the best explanation, but it's better than nothing, right? So, okay. So, we got our, so this is our table of steps. We got a table of steps. We got a table of masks. And we also need a table of shift amounts. And also, we got to figure out what these are, right? We don't know what these are yet. So, let's just put some X's here. We don't know what those are yet. We'll have to figure that out. And we also need a, this also needs to be a U32 if they're masks. We also need to figure out, what do we need to figure out here? We need to figure out the shift amounts, right? So, we need a table of, we already have, S for, for step amount. So, maybe we should just call this, instead of calling it table SA, we might want to call it table of off, right? Because, table offset amount, right? We might want to call it offset amount just because then we can have offsets, we can have masks, and then we can call this she for shift, right? So instead of step amount and shift amount, right? SA is kind of ambiguous. So SA is ambiguous. SA shift amount. SA. Right, so SA is kind of ambiguous. So we're going to use, we don't know what that is, so we'll use table of offsets. And for step amount, we can use, oh, sorry. For shift amount, we'll use table of shifts, right? And for step amount, we'll use table of offset, right? And I think that'll make things a little bit easier to understand. So we have a reason for why we're going to kind of like give that a different name that it already has. So @vid IID. And also, today is not Monday, is it? Today is like Tuesday, isn't it? Ah! Okay, well... We got the video number right, so I'm not going to stop the stream and erase this from the archives, because we already recorded some stuff, and I didn't get it wrong enough to say that the most important thing is this integer ID. So I'm not going to worry that that the day was wrong. I changed the day to Tuesday. That sucks that I got that part wrong. But the most important thing is this video integer ID in the bottom right-hand corner. So I'm not going to worry about that too much. 35, and let's do 42 because we want to be cool. Okay, so yeah, right here, originally we were going to use the variable SA, but turns out that that's a little bit too ambiguous. So is SA shift amount or is it step amount? So use tab she for table of shifts and tab off for table of offsets. The offsets are for the step amounts, while the she is for the shift amounts, right? So we can make these tables. And for the shift amounts, we just want to say, we want 2 times 0. And then we want 2 times 1. So 3, 4, 5, 6, 7, 8. So you want... So for the shift amounts, the shift amount is TE times, so the tile size exponent times 2 equals shift amount, right? Or I guess maybe we should do this 2 times tile size exponent equals the shift amount, or 2 times tile size exponent equals shift amount, right? Because we can use tilx or we can use TE for shift amount. And we might want to make a note of that, right? That for these things here, now hold on here though. So are we shifting anything out, or are we just masking things? Because I don't know if we actually need this shift thing. So let's look over here. So we have this little mask. Yeah, there's no reason to... We don't have to actually shift anything. We don't have to shift anything out. Right? We're just going to mask it, right? So we're just going to mask with the bits that we can trust. There's no shifting logic that needs to be done here, right? Because this test up here... Right, the test that we're writing is just a cut and paste of this test up here that I'm looking at right now, with just some modifications to kind of batch it up and do it, and we're just trying to do this test, but more thoroughly, with more values. Okay. So actually, we don't actually need a table of shift amounts. So we can say, so we can make a note of this. Don't need shift table. Right, so we don't need a shift table. So we can kind of comment that out. Say, we don't need a shift table, right? We don't need a shift table. I was wrong about that. We can make a little note of that. Let's say 39. Yeah, we do not need a table of shift values. All we need are these mask values, so we have to calculate these, though. Now, we could procedurally generate these values, right? We could actually... this is kind of the dumb way to do it, but the idea is that we want the test code to be kind of readable. And the more procedural nonsense that we add on to here... Right, we could generate this on the fly, we could generate this on the fly, we could generate all these things on the fly, and we could make our tests even more compact, but then it's going to be harder to wrap our head around, right? Because by procedurally generating these, what we're doing is we are manually compressing data, right? That's what we're really doing, right? So, and the more we manually compress data, the more we have to mentally uncompress it later when we're reasoning about it, right? So we want these tests to be easy to reason about, and that is why this is hard-coded, right? So at vid IID 0108, and the time is 40 and 20. 4023, how about? Hard-coded, because if we generate these on the fly, the tests become harder to mentally reason about. Right, so the reason why these values are generated on the fly, the reason these values are generated on the fly, as well as the values up here are generated on the fly, is because if we don't generate them on the fly, we just add more mental indirection, and it just makes things harder to understand when we're reasoning about the test, right? So we can say, you know, above and below. So we have the table of offsets and the masking table, right? So both of those tables are being generated on the fly, this one and that one. And the reason for that is just we want to be able to comprehend what's going on, right? Okay, so let's get to these masking values. So let's say, okay, so we got one that's 3, right? So we got that done. And we want to look at the hex values up here. So 3, okay, how about over here? Okay, we got F. So we got 3, we got F. How about over here? We got 3F. We got 3F over here. Okay, 3F. Okay, what about this? FF, that actually makes sense. Okay, what about here? We got 3FF. So 3FF. How about now? We got FFF. Okay, what about now? We got 3 and a whole bunch more Fs. So 3FFF. What about now? Just a whole bunch of Fs? Okay. So now let's trail some zeros on there to normalize this. And the pattern is pretty consistent, right? So 3 and F. 3 and F. I expected these ones. I was kind of like, I did not expect to see a pattern of 3 and F like this. Actually, that kind of makes sense now, right? 3 and F, FF, 3 FF, FFFF, 3 FFF, right? So this pattern is pretty consistent, right? It's not a big shocker as to why this table has the values that it does. And yes, we could shift these into place while we're doing it, but this is just going to make things a little bit easier for us, right? So now that we have this table of values, well, we're going to, what we are going to do is, because this is a cut and paste of a previous test, we are going to take like, we could make a hard-coded table of this kind of data, but I think for now, we're just going to auto-generate it, right? We're going to loop through it once, auto-generate it, loop through it again, auto-generate it, and then we're going to check with a certain mask value depending on what the step size was, right? So we're going to need some type of variable for masking, and I think I may have already made one, but let's look up here for a second. So up here we have... we thought we wanted this for step amount, but now we're just going to use offsets for, right? And then we had another thing for int32 for offsets, and then u32 for mask, right? So we have a table called bit masking. Now, this mask thing, it should be 16 bits, right? This is 16 bits, right? So, bit masking, 16 bits. So, right. So we're going into the table of offset, or the table of masked, and we're going to get a different number, and that's how we're kind of retrieving these, right? Okay, so off and mask, right? So then for our test here, we need to loop through all this stuff, right? So we need to say, so we can say that we can reuse test index. So for test index equals 0, test index is less than or equal to 8 minus 1, right? So there's 8 different tests corresponding to these things here, right? To these tables here that have 8 entries in them. And the test index is going to go up linearly. Okay. And each time we have a different test index, we're going to load different values from these tables. So offset equals the table offsets using the test index. And also, the mask value equals the table of masks with the test index value, right? So there we go. We got the offsets and we got the masks. And then right here, the CXCY, that's the thing that needs to be stepped by a different amount to avoid collisions, right? The layer in the offset, well, that's okay. That's not going to create collisions, but it's the CXCY stepping that's really going to bite us. So right here, we're going to do CX plus equal, and then we're going to do offset, right? Like that. And then here, we're going to do plus equal 1. And we're just going to do that so that we can have some similarity to be like, yes, we're going to do these by the offset, but we're going to keep these to 1, right? So we just want some uniformity in how we write this, right? And now we can take this exact piece of code right here, and we can go down here and modify the other loop, right? Because we want both of these loops, we want this loop to be exactly like this loop, right? Because we're going to just recreate the environment at which we did this when we do this to check that everything worked properly. Okay, so now that we have this and we're stepping by these different offsets, the next thing is these masks. So the mask value right here, this mask, is going to check only the bits that we know haven't been memory stomped, right? So check only the bits that we are certain have not been so when I say memory stomp is usually used with the connotation that it is a bad thing, but in this case, it is. I'm going to use that saying, it is what it is, right? It's not a mistake in this case, it's just how the system works. Right? Like if I set a pixel here, and then I set a pixel in the exact same location, and then I say, if I set a red pixel here, and then I decide in that same location I'm going to change it to blue, and then I'm going to put yellow here, and I'm going to put green here, and I can, right? Like in MS Paint, right? If at coordinate 0, 0, you set a red pixel, and then later at 0, 0, you set a blue pixel, you have effectively memory stomped, right? And that's not a mistake in what you did, it's just the reality of the situation, right? So, so we want to make a note of that this is video 108, and the time is 48, or 49. Okay. And we want enough room here, so let's just do this. Let's kind of move this over here. Yeah. So yeah, right here we're just checking. We only want to check the bits of the. We want to compare these two values, but we only want to compare the sections of those values that have not been memory stomped. And memory stomping, like I said, memory stomping is not necessarily a bad thing. It's just the way the system works, right? If, like I said, if you're in MS Paint and your canvas is 1 by 1 pixels in size, and you set a red pixel at the first and only coordinate, and then later you set a blue pixel at the first and only coordinate, you have memory stomped. It's not a mistake, it's of the system, it's just how things work, right? A memory stomp is not necessarily a bad thing, though most of the time when you see somebody talk about memory stomping, they are using it in the context of bad things, right? So mega test fail, ducks deserve to die, 2021. So if any of these things get tripped, then we have some problems on our hand. I think that this will go off without a hitch, besides any type of syntax mistake I have made, right? But besides stupid syntax mistakes, I think that this will go off without a hitch. The mask value, uint32. The offset table is int32. And one more thing, let's just make sure that the variables up here are correct types. Int32 for the offset, u32 for the mask. Actually, the mask is really an int. It's really just a 16-bit value. But if the mask is a... Yeah, let's use the proper bit width for here. Well, actually, hold on. It looks like we used... Oh, you know what? No, this is actually the proper bit width. It's only 16 bits, but we're writing this code with OpenGL in mind. And therefore, the functions themselves only use 32 bits in width, and that's why that is a U32 rather than a U16, even though it's only 16 bits, right? That's fine. Okay, cool. So let's give this a run and see if we can get this working. And if that gets working, I think I'm going to figure out how many more push-ups I have to do. And maybe do half of the push-ups I need to do, or something. I don't know. But I need to get more exercise. I don't really feel like doing any work today, but we got to do like a little bit of work every day. So let's see what happens here. Let's see what test fails. I'm hoping that the test I wrote just now doesn't fail. Like, I'm hoping... It looks like the long version of my test is getting executed. It's like right now it's coded as a 1 in 50 chance. Yeah, excellent. So we can see that the old test that I still need to fix is failing. And at this point, I'm pretty sure that this test is failing because I just didn't know what I was doing when I wrote that test, and that test is a complete mess. So I'm probably just going to gut that test, because this test, I am pretty thorough here. And it's working, right? So we could do one more master git put test. And for this git put test, we could use some type of hard-coded table of data. Because we do have a hard-coded for PAINT5D. So PAINT5D data. We put some test data somewhere. Yeah, we created data, unit test data, PAINT5D unit test data. This is kind of maybe a bad place to have it. Let's go look at that data for a second. So let's go look at the PAINT5D unit test data for a second. So in here we have a data folder, unit test data, PAINT5D unit test data. So I got these two tables designed for a different test, and the same kind of test, but not exactly. But we have these tests, right? So what we could do is we could try to run this same test one more time, but modify it so that we could modify it so that we still use these masks and we still use these offsets to step through stuff, but we for these loops, we look up this unit test data stuff, rather, right? So we could say, if we want to keep it really simple, what we could do is we could say, so B16 right here, this B16 is... If we wanted to be really lazy, so hold up here. Yeah, so what we could do here is B16, if we are on, it would be kind of a hackish way to do it, but instead of duplicating all this code, what we could do is for this B16 here that we're generating using kind of like just shifting and moving over, we could on the second iteration of all these tests start to grab from these values here, right? So we could have tests 0, 1, and 2. 0 will generate the value, 1 will take from this table, and test 2 will take from this table, right? So we could say so we could just say in here, we could say we could just say for meg for mega test index equals 0. Meg is going to be less than or equal to 3 minus 1. So 0, 1, or 2, right? Meg plus plus, right? So we're going to triple the execution time for these tests. And the first time we do this, if we just kind of like add this to the loop, right? We just for this test index, right? We just kind of do this, right? It should still work, right? Now we need to kind of like say up here, we can say meg, right? So int32 meg. We can say mega test index, and we can say that at vid iid. We can kind of explain this here. So 108 in the time, right? And for the test index, meg equals 0, or 0 equals meg generate values, and if 1 equals meg if 1 equals meg, we're going to use the big endian table. Right, so instead of generating the values, we're going to use the big endian table. And if 2 equals meg, we're going to use the little endian table, right? And if we do that, then we... Right, so the tests that we think are wrong are using this data already over here. So I want to actually use this data. So let's just reuse the data here and repurpose it to another purpose, right? Now, we're not going to mess with the size of the table here, right? Because that's just going to give us a headache if we've already hard-coded this size into other stuff. So we're not going to do that. So C P5D UTD dot underscore, right? So we're not going to mark what folder it's in. That folder might change during refactoring. That's enough. This is enough information, I think, to be able to find the table, right? So maybe I'm wrong, but I'm going to keep it like that. So meg is going to be used for mega test index. And then down where we wrote all this crazy code, we just add another outer loop. And depending on what the mega test index is, will determine how we generate this B16 value, right? And these loops here, so this first loop here and this first loop here, a lot of the stuff has to be exactly parallel, right? So we have to go through the loop exactly the same way and generate the value in the exact same way. Otherwise, the tests are going to fail. So we have to be very careful about how we're doing this with these parallel loops. And we're just going to make sure that when it fails on that last test that we don't like, that we're probably going to completely nuke pretty soon. You know, sometimes you do something and you make a stupid mistake and you just have to completely nuke it all. So I feel like my random whatever the heck code doesn't work very well, right? It takes like the system timer or something and uses that to seed a random number generator and get a random number between 0 and 50. But I feel like there's some type of deterministic kind of behavior that is happening that makes the randomness not very random. Because Because I'm pretty sure everything taking long there was because of one of my longer tests. But anyways, yeah, we see this test here. We entered it, we exited it, everything worked fine. And then this test failed, right? So all this junk here is because this test failed. And this test comes after the test we're currently writing. We're not going to worry about it right now. We're just going to worry about getting this correct. Okay, cool. So this looks pretty good. So now for B16, what we're going to do is we're going to make it a little bit more complicated for getting the B16 value. And I really don't want to make another like helper function. I want this test to be kind of very self-contained, even if that means a little bit ugly. This would be a great place for like in JavaScript where you can do like inline functions. This would be a great place for something like that, but we don't. But it's not. This isn't JavaScript though, so we can't do that. We just have to be very careful, right? We could, if we wanted to, just since this code has to be identical, right? Since this generator code has to be identical, if we really wanted to do something, we could do an include to guarantee that the blocks of code were identical, right? But now what we'll do is what we're going to do is we're going to say that, you know, if 0 equals meg, we generate B16 this way. And then if 1 equals meg, B16 equals, we're going to look up this table, and we got to remember that we're going to loop through here quite a lot. So B16++, oh, interesting. So you used B16 here and kind of plussed it and then kind of modulated it. And that's, I don't know if that's what we want to do. Okay, well, we know this B16 works here. Otherwise, B16 equals, okay, so we're gonna have to change this up a bit. We're just gonna need another incrementer value, right? So, we're just gonna say, we're just going to call it inc, right? So we're going to have to change some stuff. And so before we even kind of figure this out, we just need to, before we even do anything else, let's run this again, make sure it works. And we're going to just, you're just going to make another variable for this, right? So this B16 thing, we need to make like a intermediary variable that's just called like inc or something. And we're going to just do like inc equals 0, inc++, and then B16 will be derived from that. So B16 will be like equal to inc modulus 0x fff plus 1, rather than using, rather than having B16 be the increment value and being the byte value. I think that's just creating some bad times for us, so we're going to kind of change that as well. And this is a nice thing about code reuse in terms of cut and paste, because even though we cut and pasted from this code, we're making enough big changes to it where if we wanted to just try to reuse a function, we would be in some serious trouble right now. So yeah, so right here, all we're going to do is we're going to go up to the stuff we made for the third test chunk, and we're just going to say int32 inc, and we'll just say that time is 1 hour, 4 minutes, and 23 seconds. V16 being an increment value and a 16-bit payload makes tests too confusing, right? So really, it makes the test too confusing. It probably also makes the test too hard to work with in terms of writing them. So we just want to make this increment variable, and we want to refactor the test with the new increment variable before we make any deeper changes. We just want to go into here and rewrite this code a little bit and make sure it still works before we kind of massively rewrite it. So we're going to say inc equals 0, inc plus plus, and then right here where we get the B16 value, where we set it, we're going to do that, right? And then same thing for over here. We're going to reset inc to 0 and go through the loop in the exact same way, inc plus plus. And then when we generate B16, we want to generate in the exact same way with inc like that. Now the thing is that B16 is a unsigned value, right? Because B16 is a bit payload, right? So if B16 is an unsigned integer, we really should make inc also an unsigned integer, right? So yeah, because yeah, if we look at B16, it's somewhere around here. These B16s are U32s, so this should also be a U32 as well. So we can say, you know, must be an unsigned integer, right? This must be an unsigned integer. Now, I don't know the implications of how things would go wrong if this were not an unsigned integer, but I just know that if we want the code to be correct, this needs to be an unsigned integer. Otherwise, I'm not sure what would happen, but I know that the intention of how the code is supposed to work would be undermined as far as I'm concerned. Okay, so now we have this. I'm kind of scared. What code am I looking at? Okay, so this code here, right, we generate B16 using B16, and then in the next test down here, we have a whole bunch of commentary, and then we actually get to business, and here we're using inc, setting it to 0, incrementing it, using it to generate B16, then once again setting it to 0, incrementing it, and using it to get B16. So we're expecting the code to still pass this test that we're in, and if it passes the current test we're in, then we're going to further modify it to grab data from different tables depending on what test iteration it is. So cross your fingers, hope this works. And it's not yet 9, and 9 is when I have to take drugs, so I feel like what we're going to do is we're going to, if this works, I'm going to take some time to do some push-ups, try to get some more exercise in. I'm not actually going to stop the stream for that. Today is just kind of a slow day, and I just want to get stuff done. So let me get my hoodie off here so I can get ready to do that once this works. I'm hoping it works. Or it's going to pass on the test I'm writing. And or just stall out. It seems to me that so it still passed the test that we wrote, right? So this test right here, P5D OGL, right, with this dot thing right here. We can also make a little face if we want, right? If we're not sure, next time we can write a little face, make a little face here with some O's, right? Like that. There we go. And then up here, we could do the same thing. We can make a little face, be like, I'm not sure if that's really what I'm looking at. I'm pretty sure it is. It's a pretty unique string. But sometimes to mentally parse this is quite a job, right? So how about we just have to mentally parse this little face, right? So little face begin test, little face begin end test, right? So we got the little face thing here. I'm a little concerned. I thought that this was all the way to the end with the last character. So what's going on here? So down here, oh, I seem to have added a extra parenthesis because I was initially going to surround the little face with like parentheses, but we didn't have enough room for that because that was 2 characters. We only have 1 character left. Okay, so I see what we did there. Okay, cool. That's fine. So before we figure out how to change this fetching logic here, we're going to do some exercise. Look at our push-ups thing here. So we're at 140 from yesterday, but we want to get 100 a day done. So let's not slack off and say, oh, we only did 40 yesterday, so therefore we can slack off and do only 60 today. We actually want to at least get our 100 in. Really, we want to get 110 a day in. So the week total is still 140. So let's just try to get... I'm feeling ambitious, even though I don't feel like working, so I'm feeling like at least 50 or 60 push-ups, crunches, etc. before I come back. I don't know how long that's going to take. Or actually, no. Let's do 60, because if we do 60, then we hit 200. And I've been doing my trampoline jumps only when I hit 100, so I can just go out there, do 100 in a row, and then come back in. So we're going to do 60. And I don't know how long it's going to take us, so we're just going to open up like a little thing here. And we're going to do... we're going to open up a split timer. So we don't know how long this is going to take us. And we're going to go to we're on a push-up screen already. So yeah, we're just going to do this. We're going to try to get 60 of everything. We're going to do 60 of everything that we need to do, then go outside and do 100 jumps on the trampoline to get all of this, not all of it out of the way, but most of it out of the way, or half of it out of the way for the day. Do a little bit more code, do more push-ups, and then just be done, right? So let's try to get that out of the way.
Okay. 30 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Okay. Let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. Gotta do 15 more. We do 15 more push-ups. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7, 8, 9, 10. Okay, I got 5 more push-ups. 60 squats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. So, 1, 2, 20, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. You can get all 5 down right now. 1, 2, 3. 30 more squats. Let's just do dumbbells. 30 dumbbells. 30 squats, 30 dumbbells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. So you're gonna do 30 more squats, 30 more dumbbells. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, 30 more dumbbells. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 20 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, trampoline. Okay. I'm not done yet. I'm gonna get some tea really quick.
Okay, so I thought I could go upstairs and take tea for really quick and then turn it into a long conversation with my girlfriend. So we're gonna stop this stream and start a new one. But I did do my push-ups. So push-ups for today, 60, yeah, 60, 200, yeah. So I'm gonna start a new stream.